Hello, everybody. So thank you very much for having me here. I'm really glad to be Krakow again. And yeah, this is the time of the year when all the speakers have to come up with something to talk about. Right, so last year I've been talking about Spring and, well, various pitfalls connected to annotations, Spring Boot and stuff like that. And this year we'll be talking about something slightly different. I'm Maciej Próchniak, I'm based in Togo, in Warsaw. We are a small, more or less small software company. Yeah, and last year we've been talking about Spring, making fun of it, but today I wanted to start by saying that I really like one of the Spring annotations, and this is after technical difficulties, and this is transactional annotation. Fortunately, Jarek Ratajski is in the next room, so you cannot hear me. So I can safely say that this is very nice annotation. Because today I want to talk about a little bit about transactions. And I remember a few years ago when I was not so young developer, but not so experienced, I ventured to a project when we tried really different new technologies like event sourcing, transaction logs, CQRSs, various not really robust NoSQL databases, and it was really hard, challenging, and stressful project. And after that, I moved on to the project that was based, well, on Spring, transactional, MySQL, Postgres, and it was kind of a relief that I just can put it and forget about all this consistency, about do this projection will update before I want to use it, and so on and so forth. And for a while, I felt like on holidays. Until one kind of more complex requirement came, and that was, well, something about reservation of SIM cards and so on. And we have to dig a little deeper. And what sits deep inside annotations? Of course, parameters. And what are the parameters of transactional annotations? Well, one of them is, of course, this was our kind of class. It was nicely annotated. And we have to decide about this parameter isolation. So what to do? What shall we choose? And of course, we've chosen wisely. What did we choose? This is it, the default. This is what Spring advises. And if you look deep down inside Spring documentation, because it's well documented, what does it say? What does actual default mean? And it means, well, Spring says, I don't know. I just go to database, check your manual, and I will use the default isolation level of your database, which makes your code totally and nicely portable across MySQL, Postgres, and so on, right? Well, of course. So what in fact are the isolation levels? Well, it's kind of simple. Everybody knows that. It's like A in ACID. And the first ones are read uncommitted, read committed. Everybody knows that. These are the basic levels that allows us to remain sane, right? First is we won't read any kind of garbage from our database, and the second is that other transactions will get our updates only when we commit. Unfortunately, this is in some cases not enough, because let's look at this reservation use case, right? We want to select from some number pools to reserve our phone number, because we want to have it kind of nice. And we get a number, but unfortunately, we're on probably intercity train where Wi-Fi is not really working very well. So our friend also reserves this number, and what happens? Well, she updates that, and only after a while our internet train connection reconnects, and we also make update, right? And all the constraints are violated, bad things may happen, and this is kind of normal stuff under read committed level. So what do we do? Well, we can use some further transaction isolation levels, and ANSI standard defines two of them. One is repeatable read, and another one is serializable. Of course, here some dragons begin, right? Because the first thing is that these higher isolation levels, well, they can significantly degrade your performance, but unfortunately, especially with serializable, it turns out that it's not so it's not so obvious what does it really mean, because there's one ANSI definition that says, okay, serializable execution, it basically means that we can pretend that all the transactions were performed, well, essentially by one thread, right? So this is kind of, seems like a reasonable definition and so on. But unfortunately, ANSI standard defines isolation levels also in another way, right? It defines it by the absence of certain phenomena, right? So there's repeatable read, which prevents some kind of phenomena that may occur in read-committed isolation levels, and another phenomena that shouldn't occur in serializable isolation levels are no phantom reads. And the point is that these two definitions are almost equal. But unfortunately, only almost. And people came up with another definition that's called snapshot isolation, which is employed by quite a few databases, notably Oracle. And also Postgres a few years ago came up with yet another definition, which is called SSI, it's like single state snapshot isolation. And it says, more or less, all those isolations, it's connected to MVCC, that's architecture employed by Postgres and many, many databases currently. And it says that we can pretend that our transaction is running on our own snapshot, own copy of database. This is quite a nice definition and works pretty well also in terms with performance. Unfortunately, it turns out that there are some subtle phenomena that are possible with this isolation that are impossible with kind of this serializability definition, right? And one of them, actually the main of them, is called right skew. And let's look at another example. So let's assume that we have family account in the bank. There's husband and wife, and any of them can go kind of below zero at their balance, but the total sum of balances of their accounts must be positive, right? So here's husband, he has 30 zlotys, wife has 50. And what happens? The wife says, okay, I'm going shopping, and I'll be in the red, sorry, by minus 20 zlotys, but it's okay because my husband has 30, so totally we have 10. And then husband says, I'll go to minus 10 on my account because my wife has 50. And it turns out that this subtle phenomena can occur when we have this kind of snapshot isolation, which is treated as serializable, for example, in Oracle. Right? And then we violated some of our application constraints, right? Both transactions can commit, both can proceed, but the total sum on this family balance is now negative. So, bad thing. And what can we do with Oracle? Anybody knows? Yeah, with Oracle it's always a good thing to pay for something, but we can also do mighty select for update. And this is the thing that most of Oracle developers do. That is, we can kind of make additional log for certain rows that we won't ever want to update, or at least not now, but we want to make a log so that we are sure that, well, the invariances will be completed, right? And of course, some of you may think, okay, there's yet another way to achieve what we want to achieve, and that is by optimistic logging, right? So again, there's Spring annotation for that. And in many cases, it's kind of more enough. But what I want you to remember is that normal AC transaction isolation levels in normal SQL databases can be pretty tricky. This is a snapshot this is a screen from a project by Martin Kleppmann, very, very wise guy who tried to analyze what do various isolation levels on various database engines mean in terms of different phenomena. And if you look at the table, it's pretty complicated. It's by no means obvious what does repeatable read mean in terms of Oracle and what MySQL and so on and so forth, right? So this is a thing that I want you to remember from the first part of this first part of my talk, that ANSI SQL standards are almost 30 years ago or even more, but still these isolation levels are not so widely known, right? Some of these phenomena, right, this rise queue that I told you with connection to family accounts, were discovered actually, I think, 2 or 3 years after the standard had been, well, devised, right? So it took people some time to realize that it's not so easy. Well, let's leave ANSI SQL for a moment, because fortunately we don't have to worry about it, because we have yet another Spring annotation. And this is the one. And as is with Spring annotations, especially in Spring Boot, this enables yet another annotation. And this is the one, right? It's like disable transactions, and we are happy, and we don't have to care. Because what Mongo taught us for quite a few years was document model negates the need for ACID transactions. And 90% of applications don't need multi-document transactions at all, right? Well, and for many, many years, people read it and tried to employ Mongo in various situations. Yeah, in various situations. This is a slide from presentation of my good old friend from a few years ago. And it said, this is kind of a fragment of Mongo book. Granted, no one should be building a banking system on MongoDB. And this was one of his slides. And the next one was this one. And this was true. He really did that. And this is well-known Kuba Brdalik. You can go to his lecture on the next session. And yeah, he actually did that. And the system, I assure you, it's still working. Maybe not with Mongo, but it was OK. So, nevertheless, the years passed. And like 2 years ago, something strange happened. Because from the Mongo team came different perspective. Multi-document transactions are coming to Mongo 4.0. I think it was summer 2017 or 18. And then, with the final piece of puzzle, multi-document ACID transaction is game over, right? So it turned out that this functionality is really useful because we implemented it, right? Yeah, good for Mongo. It's almost game over, I think, with Mongo 4.2, which was released, I think, like 2 or 3 months ago. But when I read that, I thought, wait a second. I'm old enough to remember years like 210, 211, and all these conferences, they were like CAP theorem. You can't have consistency and availability. It's CAP theorem and so on and so on. And a few years after that, quite a few of more or less known databases said, OK, no. It was all wrong. We can do consistency, serializability, transactions, and performance will remain stellar, and so on. And we'll have SQL on top of that. And some of them are a bit more widely known, some not. Some probably are working, some not really. If you go to the talk of Kuba Brdalik, again, you'll hear some crazy histories about Cosmos DB, so I encourage you to do so. But let's think, what has to do exactly with CAP theorem, right? Because we've been told that, yeah, exactly, you cannot have consistency and availability at the same time, and that it was kind of mathematical theorem. We have proof. So now what? What do all those databases do? And it turns out that CAP theorem that was created by Brewer like almost 20 years ago, it's kind of difficult to formulate precisely. This is the definition that I took from some random blog. And turns out it's not essentially correct, so don't make photos. So it says consistency. Every node contains same data and at same time. At least one node must be available to serve data every time, and failure of system is very rare as partition tolerance. This is not precise definition, so let's look under the hood and see what are the real Brewer definitions, right? So when it comes to partitions, he says that to model partition tolerance, the network will be allowed to lose arbitrarily many messages from one node to another. So this is kind of quite strong assumption. Of course, we don't assume Byzantine failures, so we don't assume hackers, just some random network failures. And people soon realized that, in fact, this theorem meant that partition tolerance will occur. So we can choose either consistency or availability, right? And not consistency and availability and not having partition tolerance. So what is this consistency and availability that we have to sacrifice? So strong availability in Brewer's sense is saying that every request by non-failing node in the system, received by non-failing node in the system, must result in response, right? By any non-failing node, right? So it doesn't mean that some nodes are working. It means that all nodes that are working must produce result. Again, this is quite strong assumption, right? And what about consistency? It turns out it's also quite strong guarantees, because the consistency that he considers means that there must be a total order of all operations such that each operation looks as it was completed at single instant, that is single node. So it basically means that it's kind of more or less linearizable. Not exactly, but still. This consistency guarantees is called sequential consistency. And if you take all the assumptions that he makes, then this whole theorem is kind of like more or less simple corollary. The proof goes more or less like that. So we have our system, right? It's distributed, so we have to replicate. There are partition tolerance. So how can we replicate? Either synchronously or asynchronously. It kind of follows pretty easily that if we replicate synchronously, we lose availability. If we replicate asynchronously, we lose consistency in the event of partitions, right? So this whole theorem is not, I would say, particularly deep, but what it enables us is it makes us think about the trade-offs, about various trade-offs when we design our database systems. So the consistency that the trade-offs that Brewer talks about is availability, consistency, but also after a while people realized that it's not so easy. It's not only about availability and consistency, but also about performance metrics like throughput, latency, and so on. So it starts to become pretty complex, how to decide what are your trade-offs. And this is the real value of the CAP theorem. And in fact, if you look at Mongo from the beginning, all those trade-offs are, well, essentially present in its settings, right? If you want to write some data to Mongo, you can decide if you want to have what level of consistency do you have, right? 0, 1, or majority. And if you read, you have also some choices like local read, majority read, or linearizable read. And also the Mongo team is well aware of these trade-offs. So they wanted to, when they wanted to grow fast, the defaults were like, this is the default. We want performance. And when they got kind of larger, more demanding clients, they moved to some other defaults in their database. But this is just the example of Mongo, and it turns out that the research guys, quite a few years ago, they were called Bailey, Feteke, and some other people, they also wanted to explore what are the other possibilities of the trade-offs, right? Because all these trade-offs are kind of not binary. Not just 0, 1, we are consistent or not, but what are all the gray areas? And they came up with the notion of highly available transactions, and they set up to explore what properties can we save when we want to have availability. What levels of consistency are possible? And what parts of the availability we want to sacrifice if we want to have certain consistency guarantees. So we started with these binary definitions. One is this Brewer's sequential consistency. Another one is eventual consistency. And then they defined some more stuff. One is monotonic reads and writes, another is write follows reads. And these are kind of weak, lax properties, which can be even satisfied by having client buffering requests or writes. And there, I've put it into red because they can be satisfied without sacrificing availability. And then at the top, they define something called linearizability that is stronger guarantee than this Brewer cap stuff, because linearizability also requires that your operation, well, can be put in order, but that this order is also kind of consistent with real clock time. That is close, like milliseconds from the beginning of the world. And this is just the beginning, because they also defined another models of consistency. For example, read your writes and causal consistency, which are not so available as monotonic reads and writes. They are a little bit more powerful, but then they require our client to talk to one node, right? These orange models require kind of notional session, which says that it all be consistent and okay if our client during this session will talk to just one node of our distributed database. And it turns out, again, that Mongo followed the way. And starting with, I think, version 3.4 or something like that, they introduced a notion of session. And on the certain requirements like single thread, operation must be time-stamped, and some consistency guarantees on reads and write, we can use something like Mongo start sessions, and we can get this causal consistency. So if you make operations during one session, right, one Mongo session, which is kind of single-threaded, so it's not so, yeah, there are some restrictions, then we can have quite nice consistency guarantees. And if you think about it, well, this notion of session, about the single thread, that we have start session and end session, and consistency guarantees inside, this kind of resembles us, well, the notion of transaction, right? So we may very well wonder, what about, well, multi-document transactions? How do they fit into this model that I've shown you? So this is only the model that we can reason about consistency of a kind of one operation in, I would say, one operation transactions, right? So it's a model of considering consistency. But at the beginning, we were also talking about isolation. And mind you, these consistency models in distributed database setting are also something very different from C in ACID, right? Because consistency in ACID is more about, I don't know, not violating foreign keys and so on and so forth. And it turns out that these trees, well, unfortunately, they are separate. They do not require each other. But at the top, there's some mighty consistency guarantees for transactions with spanning multiple operations. It's called strict serializable, and it says, okay, this is the guarantee that all the operations, multi-operation transactions, will be consistent, will be totally isolated, serializable, and so on, and it will happen in real time, right? So there are a lot of possibilities and trade-offs, and if you look at some presentations from Mongo guys, and they show which levels can you achieve with Mongo with various different settings, well, you can achieve almost everything you want, right? So there are a lot of possibilities, lots of trade-offs. Yeah. And it turns out that, as I said, like 2 years ago, Mongo achieved this holy grail. First, they introduced multi-document transactions within just one shard. So you could have transactions, multi-document transactions, as long as they touch just one shard of your data. And like 2 or 3 months ago, they released Mongo 4.2, and then everything can happen, right? We have ability to use fully distributed transaction with Mongo, and life is beautiful. Well, of course, you have to read the documentation. This is the except. Yeah? Everybody read that? Understand? Well, I don't understand. So probably it's not so easy to use those transactions, but if you know what you're doing, then it's more or less okay. But still, we may think, okay, so where's the secret sauce? And for example, why did they took this quite a long time to reach multi-shard transactions? And you think about it, then multi-shard transactions are kind of different beasts from single-shard transactions. Because in Mongo, well, one shard has one special primary replica. So these one-shard transactions are almost like non-distributed transactions. They just touch one shard. But if you have multi-shard transactions, then you have really distributed database transactions. And if you think about it and live long enough, you know that there is certain algorithm or technique for dealing with such distributed transactions. And how is it called? Well, it's called mighty two-phase commit. And it turns out if you read deeply enough into Mongo blocks, that they also use some kind of form of two-phase commit to handle these multi-shard, multi-operation transactions. So you may also very well wonder, okay, so we're back to square one, right? We're back to mighty XA transaction manager, mighty MQ, Oracle and JBoss, and distributed transaction by two-phase commit. You remember that? How many of you used such form of distributed transactions? I did, and sometimes it's possible. For example, when all the components are in one server room, and the throughput is not above, I would say, few requests per minute, right? Then this setting might work with all those enterprise XA transaction managers. Unfortunately, two-phase commit is anti-availability protocol. And whilst people taught us this for quite a long time, and everybody knows it and believes it. So what happened? Why Mongo and also other database engines are using it if it's, well, apparently such a bad thing? Well, let's look at how two-phase commit is working. So we have coordinator, participants, and coordinator says, okay, I want you to agree if we committed the transaction or not. And he's saying this to the system 1 and system 2. And they answer, okay, I'm ready to commit. I'm ready to commit. And at this point, when coordinator gets the responses, the first responses, well, he says, okay, we'll really commit. And says to the systems, okay, we are agreed, commit, commit. And the other, okay, commit, commit. And they answer, yeah, I'm committing, I'm committing. And finally, it's done. So there are two problems with that. The first that you see even from this diagram, it's like a little bit chatty, right? Quite a lot of requests, high latency, and so on. But the biggest problem is, well, what happens at this point when a coordinator dies with kill 9 or something like that? And it turns out that this whole algorithm blocks at this point. So this is the kind of anti-availabilityness. So we have a problem. And fortunately, people can come up with different solutions for this problem. So if two-phase commit doesn't work properly, what can we do? We can introduce three-phase commit. There is such an algorithm. It requires even more conversations between participants, but it shouldn't block. But it was too complex, so people invented even more complex algorithms like Paxos that works pretty nicely, but I think that quite few people fully understand how it works, and Raft and so on and so on. And all of those are kind of the same class of algorithms of distributed consensus, right? So, yeah, some of them work better, some less, but still they are not very, very available. Those newer ones are more available than two-phase commit, but still availability is not achievable in that setting. So what do we do with these algorithms? I think that we can split the usages in two parts. One is homogeneous systems, distributed transactions, homogeneous system, and heterogeneous systems. And for heterogeneous systems, like we have database, MQ series, and whatever, few microservices, for example, connected, I think that two-phase commits and all those consensus algorithms in general won't work properly. So we have to resort to other solutions, like at least one idempotence, compensating actions, sagas, conflict free resolution, data types, and so on, right? So this is a classic toolbox of microservices. But on the other hand, where we have homogeneous distributed system, like, for example, distributed database or distributed message system like Kafka, we can think that they have some certain properties that we can kind of reason with a little bit more confidence. We know about them a little bit more. They are not just kind of generic two systems who have implementation of XA transactions. And so I think this is the reason why these, I would say, brave new SQL systems started to emerge a few years ago. We don't have time to go into the details, so I'll tell briefly just about two of them. And the first one was Spanner for Google. And if you look at the white papers they presented a few years ago, they did pretty bold claims. So they said that, okay, we know that people believe that two-phase commit is too expensive and so on, but we think that the developers are too stupid to handle consistency and serializability problems. So we'd better make serializable consistent transactions by default, and we'll figure out performance somehow. Yeah, so this is kind of bold claim, but they are from Google, so it worked out somehow. So how this spanner works, and again, this is distributed sharded database. And for single operations, when you write stuff to a particular shard, all the replicas, there's no single, I would say, primary replica like for Mongo, but they form this kind of distributed system with paxes on top of that. And it's more like master-master replication when we write consistently operations within each replica. And how do they do distributed transactions on multi-documents? Well, it's simple. They form yet another Paxos membership, this time for kind of all the shards that contains the operations. So, again, this architecture is not so great when it comes to latency. For example, I believe that the Cloud Spanner doesn't let you make arbitrary geo-replicated clusters because latency is kind of significant. And also, it's not essentially fully available, but it's consistent. And then Google sprinkles another layer of magic dust, this one connected with hardware. And this is something they call TrueTime API, because Google owns their server rooms, they own their cables and so on, and in their server rooms they have like GPSs, like atomic clocks, so they can provide themselves with hardware, not with software, a consistent kind of real-time clocks, right? That are, without having to communicate between themselves, they can provide them reasonable, well, real-time guarantees. And this lets this Cloud Spanner perform transactions in kind of real-time order. And that's why this whole setup lets them achieve this strict serializability, right? So we can assume that transactions not only are performed, well, more or less like one-threaded, but also in the real time, right? But this is the magic sauce done with various kinds of hardware, right? And about availability, this is another interesting claim. This is from a paper by Eric Brewer, who is the author of CAP theorem. Well, he works at Google at the moment, so, well, but still, we can believe him. And he says, if the actual availability is so high that users can ignore outages, then Spanner could justify effectively CA claim. So he says, okay, in theory, partitions will happen. But at Google, they are so rare that we can ignore them and say we are consistent and available. And if partitions occur, they say further, then there's high probability that your web page doesn't work anyway. So who cares? And this is something, well, I would say reasonable. Of course, as I said, this magic sauce is sprinkled by lots of hardware, Google's server room, Google cables, and so on and so forth. So many authors want to try to achieve the same guarantees without having to resort to these hardware additions, right? And they try to do all this stuff without two-phase commit or paxes. And a few years ago, an interesting solution appeared first as kind of research paper, and then they moved it to commercial database called FaunaDB. And then the idea is to, I would say, employ some ideas from functional programming. That is, we are doing replication in other way. First, all the clients says what do they want to do in transaction. And then there's some transaction log, central transaction log, that saves the definition of transactions, what operations will be performed, and this is done kind of centrally, but no actual reads are performed at the moment. And then this moment, the transactions must occur in this way or another. And then they are batched together and sent to real data nodes, which, because this component can deterministically say in which order the operations will be performed, they are sent asynchronously to all the replicas, and then they are executed deterministically by all the shards. So it's pretty interesting because it's like, and it works without paxes or two-phase commit. And what is interesting for me, because it resembles me quite a lot of functional programming. Because here, the definitions of transactions are more or less declarative. We split definition from execution. We cannot have any side effects inside transaction. Yeah, and we get transparent retries and whatnot. So as I said, this is not yet widely known. Some of this are in research papers. Some of these are in kind of new, fancy databases that are, for example, not yet available as open source code, so we cannot see them too much. But I think this is kind of interesting, really interesting approach. But for the last few minutes, let's get back a little bit closer to the planet Earth. But let's not get too close to AC databases. But let's move from database setting to another place where we can have transactions. And this place are messaging systems. And today, the modern messaging system is what? Is Kafka. I'm sure most of you know what Kafka is. Probably most of you used it this way or another. But let's remind what is Kafka, because it's not a database, although guys at Confluent are starting to say that. It's not JMS. It's just distributed log of events, right? So we can imagine Kafka as a set of log files where each producer just append some lines of bytes. They are replicated somehow. Let's not get into the details. And the clients can read from this replicated log files just as they want, right? And it's the nice thing about Kafka is that it's the client who decides from which position in this replicated log file it wants to start, where it wants to stop, and so on and so forth. So this gives it not only kind of simple architecture, of course the replication is pretty complex, but also it gives it many interesting properties that the creators can use to implement interesting feature, like transactions. Because most of you probably know that there were XA transactions spanning from JMS brokers to Oracle, but they didn't work too well. So Kafka also wanted at one point to be able to do such settings, and there are quite a few different use cases for that. One is consuming messages from Kafka broker, processing, and store it into some other system like database, HDFS, and so on. The other one, just like in Kafka streams, we take messages from Kafka, process it, and put it into another Kafka topic, and we want to do it kind of more or less transactional, like we want to achieve exactly once delivery. And the last case is we, for example, want to ingest data incrementally from some kind of database or files or whatever, and put it into Kafka. So, from a few versions, we can do it thanks to a new feature called transactions in Kafka. So how do they behave? Well, at first, of course, we have producers who write data, say, OK, I want to start transaction. I write some messages. And then when we have transactions in such settings, of course, we have to have transaction coordinator. When there's transaction coordinator, it has to have transactional log. And when you're in Kafka, everything is another Kafka topic, so transactionality log is another Kafka topic, and there are some nitty-gritty details about how the markers are put as additional messages into the topics and so on and so forth. But TLDR is that the first thing is that producers can produce atomically messages to different partitions, and consumers can read in kind of read committed way, so that they consume only messages that are parts of committed transactions, right? This is kind of reasonable defaults. So this is more or less how currently Kafka transactions behave. So there's this atomic producer. Consumption is on read committed level, more or less. And one caveat is that consumer can be blocked by running transactions, right? Because the messages are still in this log file, so if there's a message that's part of running transaction, then no further messages can be read until transaction is committed or aborted. And this atomic transactionality can enable Kafka to achieve exactly once delivery. So we want to read some messages, produce some messages to, for example, another Kafka topic, and do it atomically, right? Because before, Kafka just supported at least once, and now they want to support exactly once. And this is possible because usually the offsets where the consumer reads from in this Kafka topic is stored where? In another Kafka topic. So because we can do atomic write to our normal topics when we write data, and to this topic with the offsets, we get atomic transaction as a whole, which is interesting. It solves the problem for the case when we want to consume from Kafka and write to Kafka. Yeah, so we are in one failure domain. And what about the case when we want to import data from database and write it to Kafka? Well, it's also pretty simple, because atomically, transactionally, we can write not only the actual messages that we ingested from database, but also we can, for example, write to another Kafka topic in which position the database or the file we ended, right? So again, we have one commit to one Kafka. And another case, when we want to export data to database transactions, this time we have to move to the database failure domain. So we commit the offset where we ended in Kafka, not to Kafka, but this time to some auxiliary table in database. Because if we have here transactional database, we can atomically commit not only records that we read, but also the position where we finished, right? So these are kind of special cases, but I do believe that in generic cases where, for example, we want to read from Kafka and write to, I don't know, generic microservice, then we have to still resort to the notion of at least once plus, well, good of idempotence, right? So to sum up, Kafka can achieve exactly once reasonable atomicity guarantees. We cannot perform side effects, right, writing to another microservice, and we have relatively weak isolation. And to wrap up, we've talked about different things, about industry standards and research stuff. And I want you to remember that, well, the first thing is that even surprisingly simple things like AC transactions can still hide some mysteries. That if we use something, especially like database, it's good to really read the docs and try to translate the docs and marketing bullshit inside to, well, some kind of common definitions so that we know what we are really talking about. And the third thing is that, like, laws do not change. For example, the speed of light is kind of nice constraint on our latency, although I think in Spring 12 probably there will be some annotations to handle that. But constraints and trade-offs do change. And from time to time, it's good to see if the trade-offs that were made a few years ago, few systems ago, maybe they are not so viable, and we have to change our approaches. And if you want to learn something about all those stuff, I highly recommend this book by Martin Klepman. I think it was really even translated in Polish recently. And another two resources is more or less widely known, Yeps.io with various database tests, and another blog by Daniel Abadi, who's really insightful blog posts about consistency, isolation, and so on and so forth. Well, and that's all from me. Thank you very much, and I hope you'll enjoy the rest of the conference.